Hello, welcome back to the series of lectures on major theory. Today, in this lecture, we will discuss Borel major. The topic of the lecture is Borel major. Borel major. Okay. So the definition is let x tau. So there should be something with the Borel major should be defined for the Borel the sigma algebra generated by open sets, Borel sets. Okay. So for this we must take topological space. So let x tau be a topological and it's housed out topological space, and I will explain why we are taking housed out topological space in. Okay. So let x tau be a housed out topological space. Be a housed out topological space. Be a housed out topological space, and let be a sigma algebra generated by let be a sigma algebra be a sigma algebra generated by tau, the collection of open sets. So that will be a sigma algebra generated by this. A major mu from this Borel set to 0 to infinity is called a regular Borel major, is called a regular Borel major if it satisfies the following properties. If it satisfies the following properties. Property number 1, mu of k is finite for every compact subset of x. Mu of k is finite for every compact set k. For every compact subset k of x. Okay. That's the first property. The measure of compact set is always finite because we have a compact set here as x a topological space. And the second property is if B is a Borel set, if B is a Borel set, then its measure is given by, then measure of B is equal to, mu of B is equal to the infimum of mu of the open sets, while O is open. O is open, and this B is subset of O. So measure of open Borel sets given by this formula. And third property, if O is open set, every open set is Borel set, in fact. So measure of opens can be written in this form. But here is the interesting formula for open set, which is if O is open set, then its measure is given by. In fact, how to measure actually? Then its measure of O is given by, it's the supremum, not the infimum. It's the supremum. It is the supremum. It is its supremum mu k, where k is a compact set, so that k is compact and this k should be subset of O. That's the third property. So this measure, if it satisfies the measure on the Borel set, if it will satisfy these three properties, then it's called a regular measure. It's called a regular. So that's the definition of regular measure. This is called the regular Borel measure. Regular Borel measure. Okay, it's called a regular Borel measure. Next, if it satisfies one more property, a measure mu on Borel sets, a measure mu on B, the collection of Borel sets that satisfies mu of K is compact. That satisfies mu of K is compact. That satisfies mu of K is finite. Sorry, mu of K is finite for every compact set K. For every compact set K is referred to as Borel measure. This is referred to as Borel measure if the measure of every each compact set is finite. So if the measure on Borel set satisfying only this property, that measure of compact set is finite, then it's called Borel measure. And if it satisfies about three properties, compact and the second and third property also, then it's called regular Borel measure. Now next, we have a very interesting lemma, which states that if mu is a Borel measure, if mu is a regular Borel measure, satisfying it satisfies those three properties. If mu is a regular Borel measure, if mu is a regular Borel measure on topological space, so that topological space housed are it's already clear in the definition. Then the measure of the Borel set is given by, it's equal to the supremum mu of K such that K is compact, and K subset B, and K subset of B. Okay, so actually for a regular Borel measure, mu of B is this actually infima. This is the definition, but we need to show that this one actually. Mu of B is supremum of mu of K is where K is compact set and K is subset of B. For open sets, this is the definition. Okay, if B is an open set, then this is true, because for open sets, this is a property third of regular Borel measure. But we need to show that this also holds for Borel sets as well. Okay, so let's write down its proof. Let B be a Borel set. Let B be a Borel set. Let B be a Borel set with mu of B is finite. So this result is for this mu of B should be finite. Okay, this is where this mu of B while this mu of B, this is true for every Borel set B, with mu of B is finite. Okay, if mu is a regular Borel measure on topological space, then mu of B is equal to supremum of mu of K, where K is compact set and K is subset of B, and where B, this B is a Borel set such that mu of B is finite. Okay, so this mu of B is finite. Okay, with mu of B is finite. With mu of B is finite, and let epsilon be any positive number, and let epsilon be any positive number, then we can find choose an open set, choose an open set V such that B is subset of V, and this holds mu of V is less than mu of B plus epsilon. Actually, mu of V is less than mu of B plus epsilon. Okay, so this mu of B is actually infimum over the open sets actually. So if I add L epsilon to this infimum, then we can find open set V in that set such that B is subset of V, and mu of V will be less than mu of B plus epsilon. That's a property of the infimum. Okay, now this one. Now this V minus B, it's subset of now this V minus B. Now this V minus B, it is subset of V, and V minus B is a Borel set. It's also a Borel set, and its measure is also finite. Whether finite or not, we don't need finite, but it's a Borel set because V is open, therefore V is Borel, and B is Borel, and difference of two Borel sets is again a Borel set, as the collection of Borel sets is a sigma algebra, therefore collection of Borel sets is closed with respect to the difference. V is Borel set, B is Borel set, V minus B is also Borel. This is already done. Every open set is a Borel set. Okay, so V is Borel, B is Borel, V minus B is Borel, and it is subset of V. So again, I apply the definition on this V minus B because it's a Borel set. So from the definition, we can choose an open set W. Choose an open set W such that this V, which is a Borel set V minus B, is subset of W. But I choose W such that it is also this W is subset of V, such that this mu of B, mu of W is less than mu of V minus B, because mu of V minus B is the infimum of such sets plus epsilon positive. Okay, but what's mu of V minus B? It's less than epsilon. So this is equal to mu of V minus mu of B plus epsilon. This one is again less than epsilon. This is here. This mu of V minus mu of B is less than epsilon. So this is less than epsilon. Therefore, it's less than now 2 epsilon. This is less than. So mu of W is less than 2 epsilon. Mu of W is less than 2 epsilon. Mu of W is less than 2 epsilon. Okay. Next, choose a compact set. Next, choose a compact set C such that C subset of V for the open set V, because measure of open sets is given in terms of the compact set. It is supremum of over compact sets, and this holds measure of open set is less than measure of the compact set plus epsilon. Actually, measure of this open set minus epsilon is actually, you are applying the property of supremum because mu of V is the supremum of such measures. So measure of the compact set such that C is substar V. It's the definition of the Borel measure. Regular Borel measure of the open set is given by supremum of measure of compact set such that those compact sets are substar V. And if I will subtract epsilon from this supremum, mu of V, which is equal to the supremum, then I can find some compact set substar V such that measure of V, that supremum minus epsilon, is less than mu of the compact set. That's the property of supremum. I will write it here. It's property of supremum. Property of, okay, property of supremum. So next we put this K, which is equal to C intersection W complement. Then if any point in K will be in what's this K then? Then K is compact subset of B. So it's subset of B. So for if X is in K, then X is not in W. If X is not in W, here I want to see it. If X is not in W, here you can see, if X is not in W, then X is not in V minus B. So that means X must be in B. So I can write this as. So then oh sorry. Then this holds. Then X belongs to K implies X belongs to V. Therefore this K is substar V. K is substar B. Okay, this K is a substar B. Thus K is a compact substar B. Moreover, uh, 0, which is less or equal to mu of B minus mu of K, because B is bigger than K. So by monotone property of outer measure, which is equal to mu of B minus K, as mu of B is finite, so I can use this formula, mu of B minus mu of K is equal to mu of B minus K, which is less or equal to mu of V minus K, because B is substar V. By monotone property, which is equal to mu of V minus K is equal to, by substituting the value of K, which is equal to V minus C union W. You can easily verify this using the value of K here. Okay, mu of V minus C union W, which is less or equal to mu of V minus mu of C plus mu of W, which is less or equal to, using the additive properties, sigma sub additive property of the outer measure, mu of V minus C plus mu of W. And what's mu of V minus C? It's equal to mu of V minus mu of C, which implies this mu of B minus mu of K is less or equal to mu of V minus mu of C plus mu of K. But this is less than 2 epsilon. This is less than 3 epsilon now, because mu of B is also less than epsilon, and this one is less than 2 epsilon. It's less than 3 epsilon. So that means you have mu of B is less than mu of K plus 3 epsilon, or you can say this, mu of B minus 3 epsilon is less than mu of K. So for every epsilon positive, I can find a compact set K such that K is substar B, and mu of B minus epsilon, mu of B minus 3 epsilon is less than mu of K. So which implies, by the definition, by the property of supremum, which implies mu of B is equal to supremum of mu of the compact sets, such that K is compact, K is compact, K is compact, and this K, it is subset of B. It is subset of B. So this proves this theorem completely. So now we have the I can say the last theorem of this regular Borel measure, which is the Lebesgue measure on Rn, which has already been defined. The Lebesgue measure on Rn is a regular Borel measure, is a regular Borel measure. So I will leave this the proof of this theorem for you, and you can see the proof on Alfred's and Birkinshaw at page number. You can see this proof at page number. See page number 137. Okay, on Alfred's and Birkinshaw, you see this proof. It's very simple. It's not too difficult. So you have to just verify those three properties. Clearly, mu of the compact set must be finite, because every compact set is actually bounded. Every compact set of Rn is bounded, so it must be contained in certain closed interval, okay, of Rn. So that means its measure must be finite. That first property is trivial. Second is also trivial. Second is not too difficult, but you have to verify the third property. That's measure of the open set is equal to the supremum of measure of compact sets. Mu of K is a compact, and K is subset of the open set O. Thank you.